Imagine watching a galaxy die. Not through explosion or collision, but through something far more disturbing. It simply fades, star by star, nebula by nebula, until nothing remains but empty space where billions of suns once burned. In 2019, astronomers at the Hubble Space Telescope captured something that shouldn't exist. A galaxy clearly visible in earlier observations had lost 97% of its stellar mass. The stars hadn't exploded, they hadn't been stripped away by gravity, they had simply vanished, as if erased from existence itself. This wasn't an isolated incident. Across the observable universe, dozens of these phantom galaxies have been identified. Cosmic structures containing hundreds of billions of stars, disappearing on timescales that violate everything we understand about stellar evolution and galactic dynamics. The implications are staggering. If galaxies can vanish, what does this tell us about the stability of cosmic structure, about the nature of matter itself, about the ultimate fate awaiting every galaxy in the universe, including our own Milky Way? What if the universe isn't just expanding? What if it's actively erasing itself, one galaxy at a time? Today, we journey through evidence that challenges everything we thought we knew about galactic evolution, stellar populations, and the fundamental fabric of space-time. The story begins not with a dramatic discovery, but with a routine comparison. In March 2019, Dr. Peter Van Dockum at Yale University was conducting what astronomers call a deep field study, comparing archival images of distant galaxies taken decades apart. The goal was simple: measure how galaxies change over cosmic time. One galaxy caught his attention. Designated NGC 1052 DF4, it sat approximately 65 million light-years from Earth in the constellation Cetus. In images from the 1990s, it appeared as a diffuse but clearly defined ultra-diffuse galaxy, roughly the size of the Milky Way, but containing far fewer stars. Nothing remarkable. The universe contains billions of such galaxies. But when Van Dockum compared those images to recent observations from Hubble, something was profoundly wrong. The galaxy had faded dramatically. Not dimmed, as if obscured by dust. Faded, as though the stars themselves were disappearing. Think about what a galaxy actually is. It's not a single object, but a gravitationally bound system containing billions of stars, each burning through nuclear fusion, many destined to shine for trillions of years. Galaxies don't just lose stars quickly. The timescales of stellar evolution are measured in millions or billions of years. Yet, NGC 1052-DF4 had lost the equivalent of 200 billion solar masses in less than 30 years of observation. That's not dimming, that's erasure. Van Dockum's team ran every possible check. Equipment malfunction? The same fading appeared in data from multiple telescopes. Observational error? Independent teams confirmed the measurements. Some form of obscuring dust cloud? The spectroscopic data showed no evidence of absorption. The galaxy was genuinely losing its stars. To understand how impossible this is, consider the life cycle of a typical star. Our sun, an average yellow dwarf, will burn steadily for about 10 billion years. Smaller red dwarf stars can persist for trillions of years, longer than the current age of the universe. Even massive stars that die young, burning through their fuel in mere millions of years, die spectacularly. They explode as supernovae, leaving behind neutron stars or black holes, and spraying enriched material across space. Stars don't just wink out. They don't fade away like dying embers. Nuclear fusion is an all-or-nothing process. A star either burns or it doesn't. There's no gradual dissolution. Yet that's exactly what Van Dockum was observing. Not stars exploding, not stars being gravitationally stripped away by a nearby massive galaxy, stars simply ceasing to exist.
The initial hypothesis seemed reasonable. Perhaps NGC 1052-DF4 was undergoing what astronomers call tidal stripping. When a smaller galaxy passes near a massive galaxy, gravitational forces can literally tear stars away from their home galaxy, creating long stellar streams that trail through space. This happens. We've observed it countless times. The Sagittarius dwarf galaxy is currently being torn apart by the Milky Way's gravity, leaving rivers of stars in its wake. But tidal stripping has a signature. It creates visible stellar streams, tails of stars stretching away from the victim galaxy toward the predator. It's violent, but it's traceable. You can see where the stars are going. When Van Dockum's team searched for stellar streams around NGC 1052-DF4, they found nothing. No tails, no trails, no evidence of stars being pulled away. The stars weren't moving elsewhere. They were simply gone. This is where the story takes its first disturbing turn. Van Dockum published his findings in Nature in 2019, expecting a vigorous scientific debate about measurement techniques and alternative explanations. What he got instead was silence, followed by an avalanche of similar reports. Within 6 months, 3 other research teams came forward with their own phantom galaxies. Dr. Shani Danieli, working with data from the Dragonfly telephoto array, identified 2 more ultra-diffuse galaxies exhibiting the same impossible behavior. Dr. Ignacio Trujillo in Spain found evidence in archival data dating back to the 1970s, suggesting this phenomenon had been happening far longer than anyone realized. Each case followed the same pattern. Ultra-diffuse galaxies, relatively isolated in space, losing stellar mass at rates that violated conventional physics. And in each case, the missing stars left no trace. The scientific community faced an uncomfortable reality. Either every telescope, every measurement technique, and every independent observation team was making the same systematic error, or galaxies were vanishing. The possibility of widespread observational errors seemed unlikely. These weren't amateur observations with backyard telescopes. This was data from Hubble, from the Keck Observatory, from the Very Large Telescope in Chile. Different instruments, different methodologies, different teams, all seeing the same thing. Which left the other possibility. Something in our understanding of galactic dynamics, stellar populations, or the nature of matter itself was fundamentally wrong. But the evidence forces us to confront an uncomfortable possibility. What if these phantom galaxies aren't anomalies? What if they're showing us something fundamental about how the universe works? Something we've never noticed because it operates on timescales we've only recently been able to observe. The question became urgent. What's happening to the stars? Where are they going? And most troubling of all, could this happen to any galaxy, including our own? As word spread through the astronomical community, researchers began combing through decades of archival data with new eyes. What they found was disturbing. The phantom galaxy phenomenon wasn't rare. It was everywhere, hiding in plain sight. Dr. Michelle Collins at the University of Surrey analyzed data from the Sloan Digital Sky Survey, a comprehensive mapping project that has cataloged hundreds of millions of galaxies. Using an algorithm designed to flag anomalous brightness changes, her team identified 47 candidate phantom galaxies showing significant mass loss over observation periods ranging from 15 to 40 years. 47 galaxies across different regions of the sky at different distances from Earth, all exhibiting the same impossible behavior. The odds of this being observational error dropped to effectively zero. Scientists discovered specific patterns in which galaxies were affected. The phenomenon appeared exclusively in what astronomers call ultra-diffuse galaxies, or UDGs. These are strange objects, roughly the size of the Milky Way, but containing 100 times fewer stars, making them appear ghostly and translucent against the cosmic background. UDGs were already mysterious before this discovery. Nobody fully understood how they formed. Were they failed galaxies that never accumulated enough gas to form many stars? Were they normal galaxies stripped of gas by environmental effects? The debate was ongoing. Now they had another defining characteristic. They were disappearing. The scale of the mass loss was consistently staggering. The average phantom galaxy was losing stellar mass equivalent to 10 million suns per year. To put that in perspective, imagine the Earth. Now, imagine 10 million objects, each with the mass of our planet, simply ceasing to exist every single day. And this was happening not over billions of years, as stellar evolution would suggest, but over decades. In cosmic terms, this was instantaneous. A galaxy containing 100 billion stars losing them faster than new stars could possibly form. But comparison to familiar references makes the impossibility clear. Stellar formation in a typical galaxy might produce 1 to 3 new stars per year. Even in starburst galaxies, regions of intense star formation, the rate peaks at perhaps 100 stars per year. The phantom galaxies were losing stars at rates thousands of times faster than the most extreme formation rates we've ever observed. Conventional explanations began falling like dominoes. Tidal stripping? Ruled out. No stellar streams, no nearby massive galaxies, no gravitational evidence. Dust obscuration? The spectroscopic signatures didn't match. Dust absorbs light at specific wavelengths, creating a characteristic dimming pattern. The phantom galaxies showed uniform fading across all wavelengths. Failed observations? Multiple independent telescopes confirmed the findings. Supernovae? A galaxy experiencing enough supernovae to account for this mass loss would be blazing with X-ray and gamma-ray emissions. The phantom galaxies were quiet, showing no unusual high-energy signatures. Each explanation, when tested against the evidence, failed completely. But this represents just one piece of a much larger puzzle. In 2021, Dr. Aaron Romanowski at San Jose State University discovered something even stranger while studying the kinematics of phantom galaxies, how their stars move. In a normal galaxy, stars orbit the galactic center following predictable patterns determined by gravity. The orbital velocities tell us about the galaxy's mass distribution. By measuring how fast stars move, we can infer how much matter must be present to generate those velocities. When Romanowski measured the kinematics of several phantom galaxies, he found velocities that didn't match their visible stellar content. The stars were moving as if the galaxy contained far more mass than telescopes could detect. This is usually evidence of dark matter, the mysterious substance that makes up 85% of the universe's matter. But here's the strange part. The velocity measurements suggested the dark matter was disappearing too. This changed everything. Dark matter doesn't interact with light or normal matter except through gravity. It doesn't burn, doesn't shine, doesn't absorb or emit radiation. It just sits there, providing the gravitational scaffolding that holds galaxies together. If dark matter was vanishing along with the stars, we weren't just dealing with a stellar phenomenon. We were dealing with something that could affect the most fundamental matter in the universe, something we barely understand to begin with. The implications were staggering. Dark matter is everywhere, making up the vast majority of the universe's mass. If something could make dark matter disappear, nothing in the universe was stable. Every galaxy, every cluster, every cosmic structure was potentially vulnerable.
The most remarkable discovery involves a phenomenon that sounds like science fiction: quantum evaporation. In 2022, Dr. Lisa Cooley at the Harvard-Smithsonian Center for Astrophysics published a paper proposing a mechanism that could, theoretically, explain the phantom galaxy phenomenon. Her hypothesis draws on quantum field theory, the bizarre physics governing the behavior of particles at the smallest scales. According to quantum mechanics, the vacuum of space isn't truly empty. It seethes with virtual particles, matter-antimatter pairs that constantly pop into existence and annihilate each other in fractions of a second. This isn't speculation, we've measured it. It's called the Casimir effect, and it's one of the strangest confirmed predictions of quantum theory. Cooley's hypothesis takes this further. She proposes that under specific conditions, the quantum vacuum can become unstable, creating what she calls evaporation zones, where normal matter spontaneously converts into virtual particles that immediately annihilate each other. Think of it like boiling water. Individual water molecules constantly evaporate from the surface, transitioning from liquid to gas. Cooley suggests that in certain regions of space, matter itself might evaporate into the quantum vacuum, disappearing from existence in the process. The conditions required for this are extreme. You'd need regions where the quantum vacuum energy exceeds a critical threshold, where the fabric of space-time itself becomes unstable. But ultra-diffuse galaxies, with their extremely low matter density and peculiar dark matter distributions, might create exactly these conditions. This sounds insane. It contradicts the conservation of energy, one of the most fundamental principles in physics, which states that energy cannot be created or destroyed, only transformed. But quantum mechanics already violates classical energy conservation on tiny scales and short timescales through the uncertainty principle. What if in these phantom galaxies, we're seeing quantum effects scaling up to cosmic proportions? What if the rules that govern atoms and subatomic particles can, under rare conditions, affect entire stars? Recent discoveries within the last 3 years support this unsettling possibility. In 2023, the James Webb Space Telescope detected unusual fluctuations in the cosmic microwave background radiation surrounding several phantom galaxies. The CMB, the afterglow of the Big Bang, should be extraordinarily uniform. Finding localized disturbances suggests something is disturbing the quantum vacuum itself. Dr. Priyamvada Natarajan at Yale analyzed these disturbances and found they exhibit a pattern consistent with vacuum decay, a theoretical process where space-time transitions to a lower energy state, like water freezing into ice. If the quantum vacuum around these galaxies is decaying, it could create the conditions for matter evaporation. The mathematical models match the observations with disturbing accuracy. The predicted rate of mass loss, the types of galaxies affected, the absence of high-energy signatures, everything aligns with the vacuum decay hypothesis. The evidence extends beyond disappearing stars into the realm of fundamental physics. If matter can evaporate through quantum processes at galaxy scales, it means the barrier between quantum mechanics and classical physics isn't as solid as we thought. For a century, physicists have struggled to reconcile quantum mechanics with general relativity. They operate on different scales with different rules, and nobody has successfully unified them. But the phantom galaxies might be showing us that there's no hard boundary. Under the right conditions, quantum weirdness can scale up. The universe at its largest scales might be subject to the same bizarre rules as the quantum realm. Consider what this means. Atoms are made of particles held together by fundamental forces.
Those forces operate according to quantum rules. If quantum effects can scale to affect entire galaxies, then every structure in the universe, from planets to stars to superclusters, is potentially subject to quantum uncertainty. Nothing is truly solid. Nothing is truly permanent. Everything exists in a quantum state, probabilistic rather than deterministic, and under the right conditions, that probability might collapse toward non-existence. The scientific theory that ties everything together is called false vacuum decay, and it's one of the most disturbing concepts in modern physics. According to quantum field theory, the universe exists in a particular vacuum state, a baseline energy level for empty space. But this might not be the lowest possible energy state. There might be a deeper, more stable vacuum state that the universe hasn't transitioned to yet. If that's true, we're living in a false vacuum, a metastable state that could, theoretically, decay at any moment. If false vacuum decay occurs, it would happen at the speed of light, propagating outward in an expanding bubble. Inside the bubble, the laws of physics would be different. Atoms might not hold together. Stars couldn't exist. Complex structure would be impossible. The phantom galaxies might be showing us localized false vacuum decay events. Dr. Katie Mack, theoretical astrophysicist at North Carolina State University and author of The End of Everything, has studied the scenario extensively. She explains that if false vacuum decay is occurring in isolated pockets rather than spreading universally, we might be observing the early stages of a much larger process. Think of it like crystals forming in supersaturated water. One crystal nucleates, then grows. Another appears elsewhere. Gradually, the entire solution crystallizes. If vacuum decay nucleates in regions of low matter density, like ultra-diffuse galaxies, we might be watching the universe gradually transition to a new vacuum state, one galaxy at a time. Leading physicists at CERN, MIT, and Cambridge have debated this interpretation vigorously. Dr. Alan Guth, who developed the theory of cosmic inflation, suggests that the phantom galaxies might be evidence of a symmetry-breaking event, similar to what happened in the first microseconds after the Big Bang, but occurring locally rather than universally. This forces us to reconsider fundamental assumptions about the stability of space-time itself. We've always assumed that the vacuum of space is stable, that the laws of physics are constant and unchanging. But quantum field theory allows for multiple vacuum states, and there's no guarantee we're in the most stable one. The philosophical implications are profound. If the vacuum can decay, if matter can simply cease to exist through quantum processes, then the universe is far more fragile than we ever imagined. We're not living in a stable cosmos, but in a metastable state that persists only because it hasn't found a lower energy configuration. Every galaxy, every star, every atom exists in a quantum state, probabilistic rather than deterministic, and under the right conditions, that probability might change. There are competing interpretations. Dr. Stacy McGaugh at Case Western University proposes an alternative, modified gravity theories. Perhaps our understanding of how gravity works at galactic scales is incomplete. Perhaps ultra-diffuse galaxies exist in a regime where gravitational effects we don't understand can cause apparent mass loss. This would be revolutionary in a different way, suggesting that Einstein's general relativity needs modification for low-density environments. But even this interpretation leads to unsettling conclusions about the fundamental nature of spacetime. Recent breakthroughs suggest we're approaching a critical point in understanding this phenomenon. The Nancy Grace Roman Space Telescope, scheduled to launch in 2027, will conduct the most comprehensive survey of ultra-diffuse galaxies ever attempted. With a field of view 100 times larger than Hubble's, it will identify thousands of potential phantom galaxies and track their evolution in unprecedented detail. Dr. Jennifer Lotz at the Space Telescope Science Institute leads the survey team. Their goal is to create a temporal map of galaxy evolution, observing enough systems to determine whether the phantom galaxy phenomenon is accelerating, stable, or declining over cosmic time. If it's accelerating, if more galaxies are vanishing now than in the past, it suggests we're witnessing a universe-wide transition. The implications would be apocalyptic.
Ground-based observatories are joining the hunt. The Veracruz-Rubin Observatory, which achieved first light in 2024, scans the entire visible sky every few nights. This cadence allows astronomers to detect changes in stellar brightness on timescales as short as days or weeks. Within the first year of operation, the Rubin Observatory detected 17 new candidate phantom galaxies and found something unexpected: rapid fluctuations in stellar mass. Some galaxies appeared to lose stars in bursts, dimming significantly over just a few weeks before stabilizing. Others showed a steady, inexorable decline. This variability suggests the underlying mechanism might be triggered by specific events, perhaps disturbances in the dark matter distribution, perhaps interactions with cosmic rays or high-energy particles we haven't identified yet. What technologies might help solve remaining mysteries? The answer lies in gravitational wave astronomy. LIGO, Virgo, and the upcoming LISA space-based detector can sense ripples in space-time caused by massive cosmic events. If matter is truly evaporating through vacuum decay, it should produce detectable gravitational waves. The transition from a false vacuum to a true vacuum would release enormous energy, creating characteristic signatures in the gravitational wave spectrum. Dr. Karen Jani at Vanderbilt University is developing detection algorithms specific.
Dr. Karan Jani at Vanderbilt University is developing detection algorithms specifically designed to identify vacuum decay signatures. If successful, we might be able to observe the quantum evaporation process directly, watching space-time itself restructure at the moment of transition. The predictions are stark. If the phantom galaxy phenomenon represents localized vacuum decay, and if these events are nucleation points for larger transitions, we could be living in a universe approaching a phase transition. Computer simulations run by Dr. Matthew Claban at New York University model how vacuum decay bubbles might propagate. In most scenarios, once vacuum decay nucleates, it spreads exponentially. But in a small subset of simulations, the decay remains localized when it occurs in low-density regions, creating isolated pockets of altered physics. The phantom galaxies might exist in these pockets, regions where the laws of physics have already changed. The stars aren't disappearing. They're transitioning to a state where they cannot exist under the new physical laws. Connect this to broader questions about the universe's fate. Cosmologists have long debated how the universe will end. Will it expand forever, growing cold and dark in the heat death scenario? Will it collapse in a big crunch? Will dark energy tear everything apart in a big rip? The phantom galaxies suggests a fourth possibility: the big transition. Not a violent end, but a gradual restructuring, as the universe transitions from its current vacuum state to something fundamentally different. Matter dissolves not through expansion or collapse, but through quantum evaporation, erasing matter itself from existence. What this means for us is impossible to calculate with current data. If vacuum decay propagates at light speed, we'd have no warning. One moment we exist, the next, we transition to a state where existence in our current form is impossible. But if decay remains localized, we might observe the universe slowly dissolving around us over billions of years, phantom galaxies serving as cosmic gravestones, marking regions where the old physics no longer apply.